Hello, my name is Ming. Today I'm going to present our project, Phylogenetic Inference with GFlowNets. This is joint work with Zhou Yan, Elliot Lane, Marcel Blanchet, Nikolai Markin, Dinhuai Zhang, Mark Zhang, and Yashua Benjo at McGill University and Mila. Phylogenetic inference is one of the most studied topics in the field of computational biology. In this project, we applied GFlowNet, a generative model proposed by Benjo et al. In 2021 on the parsimony-based phylogenetic inference. GFlowNet has shown great success in generating diverse objects in multiple tasks, including drug molecule design and biological sequence design. With GFlowNet, we aim to sample diverse phylogenetic trees with low parsimony scores. To briefly review the parsimony-based phylogenetic analysis, given a multi-sequence alignment, the parsimony methods aim to find a tree which minimizes the total number of evolution mutations to pass from one sequence to another on the branches of the tree. The classical computer science problem for this task is called the large parsimony problem. It is a challenging task as the problem is NP hard. For the scope of this talk, any mutation have a score of 1, hence the parsimony score equals to the total number of mutations. Therefore, with GFlowNet, the goal is to generate diverse phylogenetic trees with low mutations. In particular, the model should sample all minimum parsimony trees with significant probability. For large parsimony problem, the existing method can be grouped into multiple categories. The first set are the exact methods like branch and bond. Since large parsimony problem is NP hard, these methods are not efficient. There are also heuristic algorithms that perform greedy search with different branch swapping mechanisms. These methods may quickly discover suboptimal solutions, but may actually miss the optimal tree. There is also MCMC that also aims to sample diverse low parsimony trees. However, MCMC may easily get stuck at the local minimum and fail to sample diverse examples. We will now introduce the generative flow networks. To give a short summary, given a data space of compositional structure X and a reward function R that maps every element in X to a positive real number, GFlowNet is a generative model that samples from X through a sequence of actions. Moreover, the sampling probability P is proportional to the reward R. The data space needs to be compositional, which means that an object can be constructed sequentially through a consistent procedure, and GFlowNet will follow such procedure to sample data. The reward function R is predefined by the user. And the goal of GFlowNet is to sample proportional to the reward rather than obtaining the optimal object. The sampling procedure is modeled within an acyclic directed graph with a source and a sink. A trajectory from the source to sink represents the construction of one sample. All states except the sink represent a partial construct, and the states that are one step away from the sink are all objects in the data space. GFlowNet generates elements by sampling trajectories from the source to the sink. At a given state, the GFlowNet action model will produce a distribution pi over all available actions. Then one action will be sampled, and we apply the action to obtain the next state. We'll continue the procedure until a full entry is built. The probability of sampling an object X is then the sum of probabilities to sample trajectories that end at X. GFlowNet action model is a neural network to be optimized. After it's properly trained, the sampling probability will be proportional to the reward. Now let's apply GFlowNets on phylogenetic inference. We know with GFlowNet, it requires a sequential procedure to construct objects. So let's first talk about how we construct phylogenetic trees. Given a set of taxa, we construct a phylogenetic tree by iteratively joining pair of subtrees in the following steps. First, we choose a subtree from the set as a candidate to be joined. Then we choose a subtree from the rest to join with the candidate. At this point, number of trees in the set is reduced by 1, and we will repeat the same procedure until a full tree is built. With this construction procedure, we're now ready to talk about the GFlowNet setup. The source state consists of the set of initial taxa. The sink state represents the termination. The state that is one step away from the sink is a fully constructed phylogenetic tree. We have two types of states. Type 1 state consists of a set of subtrees. Type 2 state consists of a candidate subtree plus a set of subtrees. For the GFlowNet agent, at any state, the action is to choose from one of the subtrees, either to be a candidate or to join with a candidate. Now let's talk about how to model all this numerically. A state is just a set of phylogenetic trees. So first, let's discuss how to represent a single tree. We generate a representation mimicking the feature algorithm. Remind that feature algorithm is an efficient method to calculate parsimony score. It records a set of possible nucleotides working from bottom up. If children's nucleotides have overlap, the parent will take the overlap. Otherwise, the parent will take the union of children's nucleotide. We use one-hot encoding to represent a leaf node nucleotide. And for parent node, we use the corresponding bit features to represent the presence of possible nucleotides. And finally, to represent a tree, we use the bit feature as the root. This is an efficient feature because this feature provides enough information for the agent to continue the construction and calculate additional parsimony scores. A state is then represented by the set of subtree features. With the type 2 state, the candidate subtree is marked separately. The action model is a neural network that takes the input of states representation and output probability logits of each subtree. Since the input is a set, we use transformer as a backbone. Our goal is to sample diverse phylogenetic trees with low total mutations. Therefore, given a tree with mutation m, the reward function is defined as e at the power of negative m divided by s. S is a positive hyperparameter. It can be seen as statistical temperature. The lower we set it, the more likely we will sample low mutation trees. To train a GFlowNet, we follow a similar procedure as training a reinforcement learning agent. We'll sample a set of trajectories. For each trajectory, we optimize the network with a loss function. In this case, we use the trajectory balance loss. We haven't discussed the GFlowNet learning, so this equation may look unfamiliar to you. However, there are two terms we have mentioned. PF is the forward transition probability. This is obtained from the action model. R is the reward score of the tree constructed with a given trajectory. Now let's look at some results. First, we do a sanity check on a small-scale problem to show the idea is sound. We use the first 10 taxa of the dataset collected by Hedge et al. In 1990. These are RNA sequences with 1949 nucleotides. There are in total 34 million possible trees in the data space. Also, in terms of GFlowNet, there are more than 10 at the power 19 number of trajectories. The left graph shows the log rewards versus log sampling probability for a large set of trees. This shows that our GFlowNet learns a good sampler that can sample trees proportional to the rewards. The right graph shows the distribution of sampled trees' total mutations. We plot 4 histograms with GFlowNet trained with 4 different S values. Remind that with smaller S, we should have a sampler that is more concentrated on the low mutation trees, and this is indeed the case. Next, We apply our method on a large-scale problem. We look at the benchmark dataset curated from Roseman et al. In 2001. It features 64 sequences of length 1008. This is a large problem. There are more than 10 to the power of 109 phylogenetic trees in the sample space. We apply PopStar on the dataset. It obtains 21 unrooted phylo trees with the same lowest parsimony score. Based on the Robinson-Falls distance, these trees form two clusters. Results generated from PopStar serves as a baseline for us to compare. Our trained GFlowNet should at least be able to sample these 21 trees with significant probability. We train the GFlowNet with S equals 0.25. We train 200,000 steps with batch size equal to 64. On the left plots, we plot the log rewards against sampling probability. One can see that although we did not learn perfect sampler, we do sample objects proportional to the rewards. The right plot shows the log probability of sampling each of the 21 trees obtained from PopStar. This shows that we are able to sample them with significant probability. However, we can also see that there are some variations among the probability scores. This suggests that the optimization hasn't been fully converged yet, and the model can benefit from further training. This project is still in progress, so finally let's briefly discuss the directions we are working on. Firstly, we are working on improving the GFlowNet training speed by incorporating intermediate rewards. Secondly, we are working on conditional GFlowNet that can take the scale parameter as an input at inference time. Thirdly, we are working on extending our method to the likelihood-based inference by incorporating continuous variables such as edge lengths. Thank you for listening to our presentation. We thank all members of Blanchet Lab for providing useful advices on the presentation, and we will also thank the funding agencies.